Right, so we're going to talk a little bit about distance and position graphs, what information we can get from them and how we use them to analyze motion. We're going to talk more specifically about general shapes of graphs later, but right now we're going to talk about using the graphs and what information we can get to them rather than looking at what the shapes mean in matching graphs. We'll do that in a different series of videos. So for the graph that I have here, what you can see is we start at position at A, where we've traveled no distance, and then B, we've traveled 1 meter. C, we've still traveled only 1 meter. D, we've traveled 3, and so on. So things to note about distance graphs. Since distance is a scalar, and we can't show direction, that means that this graph can only increase, right? A graph of distance will never go back down towards 0, right? You can't untravel distance that you've already traveled. So what can we get from this? Well, you can tell how much distance has been traveled at each point, right? Distance at each point. You can also tell the distance between points. So for example, the distance traveled between points C and F would be 8 meters minus 1 meter, or 7 meters. Okay. We could also get speeds. Note that we can't get velocities, right? We can get average speeds. Now, how do you do that? Well, it's simple as distance over time. Okay, so we can get the average speed for interval, say the interval A to B. That would be 1 meter over 1 second, or 1 meter per second. We can get the average speed for interval EF. That would be 1, 2, 3, 4 meters over 1 second, or 4 meters per second. All right. So these are the things you can do with distance graphs. You can see how far the object has traveled at some point. You can tell how far it goes between 2 points, and you can also get average speeds. There are a few other things you can do with distance graphs in terms of noting their shapes, but by and large, these are the major uses that we're going to be looking at. Now, let's contrast this with a graph of position. Notice I'm using position and not displacement, right? Position is a little more precise of a way to define what these graphs are really showing, okay? A displacement graph would probably only be useful if we were always assuming that our initial position is 0, okay? So a displacement graph would tell you how far you are away from some specific position at any point in time, whereas a position graph tells us exactly where we are relative to our 0 position at any point in time. So again, we have points A, B, C, D, and E. However, notice that this graph goes up and down, right, and can go below the x-axis. So anytime you're going away from the x-axis, right? So away from x-axis, you're getting farther from starting point. And if you're going towards the x-axis, you're getting closer. And this is all relative to whatever the starting point is, right? So our object starts out at position A. We'll call this position A. Then they move away from position A in the positive direction to position B. And position B is 3 meters to the right of position A. Then they go back towards the origin, and position C is at the same point, is at the same position as point A. Then they go to the left of the origin to point D, and point D is 4 meters to the left of our 0 position, which is where A and C are. Okay, so when is the object not moving? Well, the object is not moving when there's no change in position. So during this interval right here, there'd be no speed, right? When is the object going fastest? Well, wherever the slope of the graph is the greatest, this is where the object is traveling fastest. So here we would have the fastest speed. Note that the speed for interval AB is the same as the speed for interval BC. However, they're not the same velocities, right? From A to B, you would have a positive velocity, and from B to C, you'd have a negative velocity because you're traveling in the positive direction and in the negative direction. And here you'd have a negative velocity because you're traveling in the negative direction. And we can calculate those speeds and or velocities the same way you calculate them on the distance graph, right? So our speed for interval AB would be the distance of 3 meters divided by 3 seconds, or plus 1 meter per second. That would be the velocity or the speed. For interval BC, the displacement, if you want the velocity, you need to put in the change in position, which is negative 3 meters over 1 second for a velocity of 3 seconds, negative 1 meter per second. Whereas interval CD would be negative 4 meters per second. Okay. Note that positive slope, negative slope, 0 slope. So moving in the positive direction, moving in the negative direction, moving in the negative direction, and then not moving at all. And if we go back to our distance graph, we can see some similarities. BC, no motion. DE, no motion. FG, no motion. HI, no motion. But here we're moving, right? And then we're moving fastest here. Looks like 1 meter per second, 1 meter per second, and 1 meter. So the speeds for all 3 of the other intervals would be the same. They'd all be 1 meter per second. And here we'd be moving at, looks like 4 meters per second. So there you go. Just a quick introduction to your distance and displacement graphs.